ocean dynamics with Christopher, myself, and other people. He comes out from Australia, but he's French. And you know him from some visits, I think, 2 years ago. So welcome.
We have a second French just arrived, my friend Lenormand. He will be here as a postdoc working in the project in Lawyer on modeling of urbanism, especially working with Jose. So welcome. I see there is a fight between the number of Germans and French. Welcome.
Just as many Italians.
No.
So it's a pleasure, and I'm saying that because I really feel it's a pleasure for me and for you guys to have here Professor Gunton. I've introduced him sometimes here, okay? And he always said I say too many things. Okay, so I try to summarize, which is difficult to summarize what he represents in physics and also in the science of statistical mechanics. And also for many of us, he's been some of us, Maxi, me, and Tony have been postdocs with him in his Temple University at the University. We know him very well, what he has represented for us, how much he has helped us during our careers. Well, he has a degree in physics and chemistry, so that's together with some of our colleagues of our department. But he has a PhD in physics from Stanford University. He has been in many places, in Australia, or in Europe, and Japan. But nowadays he's in Lehigh University. He's a professor, Joseph Wortman Professor of Physics at Lehigh University. Lehigh is a university in Bethlehem, which is north of Philadelphia, or 80 kilometers north of Philadelphia. And before he was at Temple at Philadelphia, where most of us got to know him. He has been, one of the leading forces, one of the leading scientists in the field of statistical mechanics in the 70s with all the development of the ellipsoid group, critical inequalities that bear his name, then later in the kinetics of exponentiations, then later in quantum transport, and later in so many things that we don't want to for a while he went to the dark side. He's taken to administration for a couple of years. He felt he was missing physics so much that he, or whatever, no, he quit administration almost completely. He cannot go completely, but he just quit administration formally, and now he's just a professor of physics. He's a professor of physics. Okay, he's been a regular visitor of our institute. In fact, he's a member of our International Advisory Committee, so we try to treat him well, so please do. And so he's been here many times with different programs. Once he wrote this Incompatible professorship program, which is very competitive. He's also a fellow of the American Society. Now he's in sabbatical. I say he's in sabbatical, working more than ever. Okay. He has over 200 papers. So extremely well-cited papers. Has written 2 books, one on the introduction to the dynamics of metastable and unstable states with Michel Cross, which is something you also know. Another more recent one on protein condensation. He has papers with Maxi, with me, with Jose Maria and Sancho, with Emilio, with Tony, with Claudio, I don't know where somebody else? Okay, so, we just got to know one of our papers. He said that I told him, but I don't remember telling that to him. One of our papers in neurophysics has been quoted as one of the 10 most highly cited papers in neurophysics literature. Kind of proud of it. Okay. Today he will tell us about these topics in self-assembling systems.
I'm always embarrassed when and I'm delighted to be here. Before I begin my talk, though, I wanted to say a few words about Maxi. It's been a few years ago, I won't say how many, when I first met Maxi at the University of Barcelona and at the famous Sistemas summer school in statistical mechanics that Luis Garrido ran. And then he arrived in Philadelphia, and I remember this date very vividly. I went to meet him at the Philadelphia airport. It's been a long, exhausting flight for them, and it was dark, and Maxi Paloma arrived, and on his back is a little backpack. And I looked in it, and in it is a little baby. And that little baby is now about this much tall. And I've given Maxie a grandson, and we'll soon give him a granddaughter. Maxie has just been a wonderful scholar. I remember not long after we were committed at Temple, I went to Geneva on sabbatical, and I expected to finish a review article that 3 of us were working on by myself. All of a sudden, Maxie arrived with another backpack, just on her clothes, telling me he was there to help me finish it. She did. So I've been following his career for a long time with great pride and affection. And the reason I'm saying these things is partly I feel them, but secondly, since I was here last time, he was awarded the prize from the Royal Spanish Society, which, as we would say in the States, is a big deal. And I just want to congratulate him. It's been well-deserved and long overdue, and I respect his leadership, his friendship, and his scholarship. And I just want to say that in public.
Thank you.
Okay. Today I want to talk about self-assembling systems. And I'm going to try to cover 2 topics. One is something that's a relatively big area in the States. I'm not sure so much is going on in Europe. What I call man-made Janus particles. I'll spend quite a bit of time on that. Our group has been involved in recent research in that. And then I'll talk about something called amelogenin protein molecules, which are involved in dental enamel formation. I don't know if Tony's here. Tony was involved in this research before he had the whiskers. So I'll talk about both of these in some detail. Just to remind you, Janus was in mythology the two-faced god, and has become famous in science more recently because Pierre Duchenne, when he won the Nobel Prize in the 20th century, in his acceptance speech, proposed that people start making two-phase particles and exploit the properties of these particles so that they could be used in various ways. In his case, he was particularly interested in surfactants, molecules that could sit at the surface between an oil and water interface, for example. And it took a while before people paid attention to him, but eventually some really clever chemists learned how to make these. And they now come in all flavors. The one that's been most studied are these Janus spheres by Steve Granick's group at the University of Illinois. But there are many other varieties that have been made, and we have been studying, as I will tell you, spheroids. And you can coat them with different things. Typically, one side is coated in such a way that it's hydrophobic, which means that it doesn't like water. So if you put 2 of these particles in water, say, they tend to attract each other to get out of the way of water. And the other side is often hydrophilic with some electrical charge. And so people then control the salt concentration in order to control the divide screening length. They've been also studied with magnetic charges and a variety of other things that are currently going on. They're very interesting because they have a lot of practical applications. And I'm not a practical person, so I'm not the one to tell you about it. But actually, we have proposed that there is one way of using them in drug delivery, and we're not the only group. I was on a bioengineering search committee this spring, and I was amazed at how many young scientists are coming out now from physics and chemistry and medicine trying to find novel ways of drug delivery. So I'll tell you about our idea as we go on. Photonic crystals has been a holy grail in the field for some time, and people think that they're getting closer to building such machines. And basically what one does scientifically is trying to understand the role that anisotropy, these building materials, plays in order to design materials that have the properties that you want. And that means that typically you're dealing with non-isotropic interactions, that the interaction between these particles depends on the orientation of the particles, which makes it a little bit more difficult to study. So the typical starting point were these Janus spheres. Let's say, that on one side red is hydrophobic, on the other side blue is, say, hydrophilic. That's the type of model that Steve Granite's group first designed and have been studying in some detail. And they have rather, I hope I can convince you, rather unusual properties. So, for example, they showed early on that you could form different types of aggregates out of these. And one of the first things that they showed was that you could form micelles, because micelles have, in this case, the attractive regions pointing inward, and then there is a repulsive layer on the surface, and that actually often stabilizes this so it has no further growth. You can grow more complex things like you have in biology, like lipid bilayers, for example, vesicles and things of this sort. You can form chains of many different varieties. This is another one from his article in Physics Today. But more interestingly, he showed people that he could build a crystal. And this was an example of a Kagami crystal. Now, this is not really, strictly speaking, a Janus particle, because what they did was to make a tri-block system. So the top and bottom were hydrophobic, and then the centerpiece was hydrophilic charge. And they could control the device screening length by putting salt in. So if you had the two hydrophilic faces opposing each other, they would repel. If you had, say, two of the hydrophobic faces toward each other, they will attract. And you could, for example, if you control the repulsion part with salt, you could build, for example, chains like this. Here is what they actually constructed of a Kagami lattice. And if you look at this section, which is blown up over here, you'll see what I mean by a Kagami lattice. It consists of these two triangles that are overlapping. And to understand how these molecules assemble to do that, if you look, for example, at these top three in this upper piece, that corresponds to these three molecules attracting each other in that way. If you look at these three next to it on the side, that corresponds to these three. And out of that basic building block, you can construct this lattice. A very clever example. They've done many other things, some of which I haven't been following. Now, Sharon Glotzer and some of her colleagues wrote an article in which they pointed out that one needed to start exploring the various dimensions that could control the design of these materials, and one of them was just the geometry itself. So we started looking at these Janus ellipsoids. We actually looked at the spheroids, where two of the axes are equal and the third is unequal. And the ratio of the unequal to the one of the two equal axes defines the aspect ratio. And so you can have either oblate or prolate spheroids. So in this model, you have a normal vector going through the center of the attractive patches. We call those, say, U's. And then there's a center-to-center distance between these, which is Rij, for the two particles I and J. And the question is, now, if you put a group of these particles together, how do they interact and what type of structure will they form? And we've only begun to explore this at low densities because it's a very complicated problem. Now, standard models that have been used for isotropic interactions in proteins, because the details really haven't mattered, are these square well models, which I just remind you what that is. The square well, this is the potential energy as a function of the separation R. You have some hardcore repulsion, and that corresponds to the diameter of, say, the sphere that you're modeling. or in this case, the larger axis of the ellipsoid. And then you would have some attractive well depth, and then the potential zero thereafter. So it's just this little region of attraction that's responsible for the hydrophobic interaction in this model. And then you control the range, which turns out to be a very important parameter, R. In Granik's work, he's chosen R to be a half. And that turns out to make computational work a lot easier. When I come to some of our more recent work, we, for reasons having to do with experiments, have made it much shorter, and that has increased the computational difficulty of some of our work. So, how do you handle this problem of trying to take a square well model, but for ellipsoids whose interaction depend on their relative orientation? And the answer is you don't. Okay? Because it turns out to be very excessively computational demanding to actually do that. It turns out the chemists, a long time ago, in many cases, 1972, developed an approximation for them to handle molecules where there were similar problems involved. And so we found this paper and we used their model. So our model consists of a potential which is infinite if the particles get too close, and then has a step function. This is the Heaviside step function with some well depth, in this case minus u0. The trick is that you introduce a parameter sigma ij that depends on the orientation of these particles. Okay? And it's such that when Rij, the separation between these centers of these ellipsoids, is greater than that distance, you have no interaction. It's an approximation, and it's been shown to work. It's been used in granular materials and other things relatively well. It's a complicated expression for sigma ij, so I won't go into that. But you can visualize what it looks like. If, for example, you look at three cases of these aspect ratios, here's an ellipsoid in the center with an aspect ratio of 0.5. Here's one over here at 0.9. That's close to the sphere. Sphere would be 1. So if you look, for example, at this situation at 0.9, the red region shows you the range of attractive interaction that a particle would feel if it were facing the red side of that particle. So you can see that the range is actually pretty constant around that particular orientation. Over here, it's relatively good approximation also. Here you can see that the approximation breaks down, that the range now, instead of being a constant value, becomes rather angular dependent, and so it's an approximation, right? But we've used that to get some of the results. This was our first paper on this, and Tony was involved in this, where we studied the oblate case for a wide range of aspect ratios. And I won't go through all the details of this, but this column here, this pair of columns, shows you what we found typically for typical clusters that you could form. So all of these will exist for an aspect ratio of 0.9, which is close to a sphere. So for example, these numbers tell you how many particles are in the cluster. So you'll see a cluster of size 3, you'll find clusters of size 4, etc., up to 13, which is more or less like a micelle. Then you get larger clusters all the way up to 72 with quite elongation in that. Likewise, if you go over to the extreme case of 0.1, then you really, I don't know what to call these things, but they're really rather weird morphologies. And you can characterize these in many ways. I'm not going to show you the results for this, but you can correlate them in terms of their relative orientation, the distribution of cluster sizes, and things of this sort. We look next.
Those clusters are static, or they move around?
They move around.
So they vibrate or they move around?
They move around, but this is what we see in an equilibrium, a typical equilibrium configuration. So we do Monte Carlo, that's an important thing. We do Monte Carlo, we run the system in equilibrium, and then we look at the clusters that are formed, and we look at the cluster distribution. and then characterize the clusters in various ways. I'm not going through all the details because it's somewhat tedious. Yeah.
So in the slide, the previous slide,
Yes.
so the three clusters, basically the separation between individual particles is due to, it's basically a dynamical average that they don't touch.
I'm
Because
sorry.
in number 3,
Number 3.
there's a distance between them. This is it.
Oops, I'm sorry. Number 3 was which one?
The left top. So here the particles don't touch. That's because it's an average of the simulation, of the dynamical simulation, or why would they locate in this way?
Oh, because of the range of the interaction bonding them.
But that is it's a Heaviside function, so there is no minimum basically inside a certain range.
I'm not sure I'm understanding the question.
Well, if
The
you
definition of being bound is that they're within a distance that's equal to this sigma ij. Is that
The question is, what determines the distance? Is this a specific distance, or is this is a random snapshot that they
this
can
is
be?
a random snapshot
okay.
showing you typical clusters.
Yeah.
Yeah.
Because in the end, in the capture range, it's a step function. There is no other clear minimum.
Right.
That's what I.
No, and you can change the potential. That's really a detail, but you still have a computational challenge
Yeah.
because of the orientational dependence.
But that's for a given temperature?
Oh yes, thank you. That's for a given temperature and for a given low density. And then you can look at different temperatures. I won't bore you with that, but we have done studies at different temperatures.
Have their phase transitions?
Yeah. I'll come to that. That's a really interesting question. Okay. Now, this is another type of, these are the prolate spheroids. And here are again two typical configurations, just to go back to what Para was asking. This is a configuration in equilibrium for an aspect ratio of 3. And we then pick out the largest cluster, and that's this one, which happens to be a very nice looking micelle. And then over here we have an aspect ratio of 10, and just to show you the types of clusters we get, again the largest cluster, which in this case is 26, as that shape. So you can really see the type of morphology you can generate from this. We have not yet gone to densities where we could form a crystal lattice. That's computationally rather difficult, and also probably involves metastability. Now, one thing you can do is you can look at the, as a measure of the order, you can look at the orientational correlation function. That is to say, you look at the n1 dot n2. n1 is, say, the normal of one of these red faces, and 2 is another one bonded to that first particle. And then you can average over the configurations you find. And for example, the clearest case here is up here, which is say epsilon equal 1 or 1.1. You find that they're pretty sharply peaked, double peaked functions. Just for clarification, if it were peaked at -1, this is peaked slightly beyond that. Peaked at -1 would mean that the two faces were facing each other. The peak over here toward +1 means the faces are parallel, but bonded. Okay? So when you have spheres, or you have slightly squished spheres, you find that there's quite a bit of orientational ordering. On the other hand, if you change the aspect ratio and say go up to 2, which is on that picture, you see that you get a broad curve, which means they're really just randomly oriented. Another way of saying it is there's a lot of entropy compared in that system compared to the more ordered state. You can look at the cluster size distribution, and for example, if you're looking at something that's like a sphere or close to a sphere, what you see is, so this is the number of clusters of a given size versus the cluster size. You see that it's here, this one, the red curve, say, it has 2 peaks. This is peaked around basically a micelle size, a stable. And this is peaked around the typical vesicle size in the stable. And then you have, of course, other clusters in the distribution. if you change the aspect ratio, you tend to start to lose this vesicle structure, and you eventually end up just with things peaked around the micelle type of structure. So the morphology depends strongly, and the cluster distribution depends strongly on the aspect ratio of these things. One lesson to be learned, if you're trying to design material like a tagging your lattice, we learned this the hard way, there can be a very sensitive dependence on a parameter. For example, we're just varying in these 3 examples. The typical clusters we find, if we start with an aspect ratio of 1.2, that's pretty much a micelle. We change it slightly, and it becomes more of an elongated thing, and then it becomes this rather linear chain, which is quite ordered inside. So there's very sharp transition between here and here. If you were trying to pick out a given type of morphology, you'd have to know where to look. Otherwise, you're doing a lot of trial and error searching. Now, they make these things. This is just published in, I think, Langner. They make now Janus spheroids. These particles, if I remember, are coated with chrome and then with gold. And there are interactions between the gold cases. And this, I'm showing you an ordered state. This is the actual confocal microscopy picture, which is magnified over here. Probably it's most clear to understand what this is by looking at this cartoon. This corresponds to the faces being ordered. As you can see, the greens tend to be interacting with the green faces. That is, the gold faces want to interact with each other. Now, you can characterize the order, not just orientationally, but you can use that to define an order parameter. So if you take that n1.n, n1.n2, and you square it, and you sum over all the pairs of bonded particles, that gives you a measure of the order. And this turns out, in this case, they use that definition. This is almost a perfectly ordered orientational system. I don't have one to show you this order, but as you would imagine, they're quite randomly oriented. Now, phase transition. Right? Let me remind you what a standard gas-liquid phase diagram looks like. This, say, the argon type, right? So the argon case would look like you lower the temperature, your gas or fluid becomes split into a gas coexisting with a liquid. It's a critical point below which this happens. And you have a nice shape of the gas-liquid coexistence curve. And over here, you notice as you cool the system, so this is temperature versus density. As you cool the system, what happens is the density of the gas decreases, right? And the density of the liquid increases. That's all standard. This is actually fullerene, not argon, but it makes the same type of point. Now, Janus spheres don't look like this. This is the Janus sphere phase diagram. So contrast that with what I just showed you. You have a critical point.
But excuse me,
Yeah.
going from one thing to this second thing, there are two different aspects. One is the anisotropy of the geometry of the molecules,
Right.
and then the fact that there is an attractive and a repulsive.
Right. Right. In this case, it's pure the two-phase part because this is spherical.
Okay.
Okay. Now, so first of all, there's a critical point, which they located here by using the renormalization group analysis and showing it within the same universality class as the IC model. IC model dominates this. I have long ago lost my interest in the renormalization group and the IC model, but you know what I mean. So they worked hard and they found the critical point. Now look at this. This is the gas phase. This is the liquid phase. What happens is I lower the temperature, the density of the gas phase actually increases. And down here, it looks as though they're going to merge into a lower critical point. Now, it turns out they can't determine that because when they get down to that low temperature, another phase which is more like a solid phase, a lamellar phase, starts to intervene, and they really can't tell if these 2 points reach equilibrium or not. This may just stop there, and there may be now a solid phase there. But why is this phase diagram so totally different from the standard gas liquid? Well, it has everything to do with the fact of the Janus particles being able to form micelles and vesicles. Because what happens, it turns out, that as soon as I get near this critical point, if you look at the gas phase, you start forming micelles. And these micelles are stable. They have the outer surface is hydrophilic, and they don't want to cluster together with any other micelle. So up here at this temperature, you have mostly stable micelles. That means the gas is energetically favorable. Normally, it's the entropy of the gas when you compete against the liquid, right? So these micelles, the fact that this gas phase is made up of these aggregates, and down here you start getting vesicles, means that the reason that a gas coexists with a liquid is totally the opposite of a standard gas-liquid phase transition. It's now the energy of the gas phase, these stable clusters of micelles and vesicles, that makes the gas phase stable. And over here, you get a percolated liquid structure which has orientational disorder, entropy, right? And they worked very hard to show this and computed one more aspect. This is just saying what I said. They calculated the pressure versus temperature. Now, you know, if the pressure, if you did this for argon, and you plotted the coexistence line at pressure versus temperature, it goes like this, right? This goes like this. That is to say, the slope of the coexistence line in this diagram is negative. If you take the Clapeyron equation, it tells you that the slope, the PdT, is related to the entropy change over the volume change, and you know that the volume of the gas is much larger than the volume of the liquid, you can easily convince yourself that the entropy of the liquid is much greater than the entropy of the gas at coexistence. The opposite of what you normally would expect. So this is a very unusual phase diagram. And that has prompted our interest in trying to see if the Janus ellipsoids have the same thing. Now, one other thing that they showed in the same paper is it's known as micellization. This is a plot of the monomer density in your system versus the total density of particles in your system. This straight line is an ideal gas. So that would say that every particle in there would be a monomer. So the density of monomers is exactly equal to the density of the particles in that system. Now imagine and these different lines are different constant temperatures. So imagine I start here along that curve, for example. Right here, I'm almost completely monomers, right? And I increase density slightly. What happens? Well, two things happen. I increase the density slightly, I get more monomers, but I also get some aggregates. And that continues all the way up. And the same is true for several of those temperatures. Until I get to a low enough temperature, say down here, where if I start with a gas of monomers and I slightly add particles to the system, I no longer have more monomers, I immediately form aggregates. Okay? So this is a very sensitive thing. This is known as the micelle transition, and it depends sensibly on temperature. So we've been trying, and we're still working on, to reproduce the phase diagram and the micelle transition for our model. Now, we haven't done the phase diagram yet, but we have a rough estimate of it because there's something called B2 scaling, which I won't bore you with, but it's a pretty good approximation that allows you to take a given phase diagram, if you know its second virial coefficient, and predict what another phase diagram in the same class should look like. And so we have done that, and this is what we expect our phase diagram to look like. And we're now doing starting detailed calculations to actually see this. But even the approximation shows you that we should expect to see the same unusual phase diagram for the ellipsoids for the same reasons as you would for the spheres. Now, unfortunately, sometimes you can destroy a graduate student's life by giving them bad advice. I've done that on more than one occasion. But this case was really stupid of me. All of the work on spheres has a range of 0.5, half the size of the particle. But all the experimentalists tell you that no, real experiments are 0.2 or so, short range, really. So I told my student last summer, let's do our problem, but we're going to do better than they did. We're going to reduce the range. All right, and of course he knew nothing, so he said, yeah. And here we are 8 or 9 months later, and he's still doing it. Why? Because it's taking us 200 million Monte Carlo steps per point to equilibrate. Because the range is so short at the low densities we're looking at, it takes forever for these particles to get close enough together to aggregate. So I'm not too popular. But this is where we are. Most of our curves look like they're above the transition point. Just before I left, we've got a set of points here that look like they're beginning to plateau. But the bad news is, and I haven't really told him this, is it looks like we're going to have to go even lower if we're going to get a reasonable estimate of this. Okay. Now, the clever idea, I think, the most interesting thing that came out of this work, I think, was because an idea of one of our graduate students, Wei Li, and a postdoc, Ya Lu. They noticed that the Janus ellipsoid micelles had one difference between the spherical micelles, and that had to do with the fact that on the inside of the inner space was much bigger for the Janus ellipsoids than for the spheres. And they had been reading about drug delivery, and they decided that maybe these ellipsoids could self-assemble and encapsulate drug particles because of this empty space. And so we took a model, a binary model now, took the same ellipsoids, so they interact with each other with some strength EE. We took the sphere as the drug particle, and it interacts with this in some strength, which we normally take to be the same as this. So sphere interacts with this. That's crucial, otherwise it won't get trapped by it. And then we included the possibility of spheres interacting with each other. And then we have done simulations. Tony was also involved in this. And here's a typical thing that we found. Now, this depends very sensitively on parameters. So we're looking at low densities, and then we vary the aspect ratio. And the results depend very much on the aspect ratio. So here is a good case where we found that if you look at these systems, both, these are two different, this is the same aspect ratio of 0.6, and these are two slightly different densities, 0.02 and 0.04. And if you look, rotate the box and everything, and say how many of these spheres are actually encapsulated versus those who are not, it turns out that all but 2 of the spheres in the box are encapsulated in each of these cases. Now the efficiency, that which they use in the drug industry, is defined as the number of spheres entrapped divided by the total number. So we had a very high efficiency, which is summarized on the next.
So the initial condition was?
I'm sorry, random.
Yeah.
Yeah, random run into equilibrium. So here's the table. I don't know if you can read this, but here's the punchline. These are the two densities I just showed you. If we look at these two aspect ratios around 0.5 and 0.6, we get efficiencies. One of them is 81.6. And that turns out to be larger than any of this in the published literature for encapsulation. So what we're trying to do now is fine-tune this so that we only encapsulate a single drug particle per encapsulation. And that's a much harder problem. But this looks like a promising method to move on. Okay, now let me tell you about your dental enamel. Tony's probably the only person in this room who knows about dental enamel now, right? At this level. And I have to say, we didn't know when we stumbled into a huge field, which I've only recently discovered. Okay? But it has to do with biomineralization. These are nanostructured composite materials that form by interactions between supramolecule assemblies of proteins, typically, and whatever the mineral is that's involved in the say the dental enamel, this apatite. And so the question is, how does this biomineralization take place at the molecular level? And that's the subject that you'd be amazed has had the interest of people, molecular biologists, for a long time, probably 30, 40 years now. Okay, and many of them are in dental schools, but they're all the ones that papers I read are first-class molecular biologists. So it turns out that dental enamel is sort of the paradigm of the field. This is the strongest mineral in our body. And basically the building blocks are these densely packed arrays of these minerals. All right? But they're also, in the beginning, of these protein molecules. And the protein molecules make up about a third of the enamel volume at the beginning. And the question is, why are they there? What roles do they play in the growth of the mineral that we call enamel? Now, it was observed a long time ago, 30 years or so ago, that if you look very carefully at these pictures around the growing mineral, they saw these, what turned out to be nanospheres. All these arrows are indicating them here. They look almost like they're beads. And likewise, if you look over here, they have another set. And when they looked more and more closely over the years, they found that always sandwiched around the mineral that was developing, guiding it, was this protein molecule. Right? Which it turned out was this protein amelogenin.
Sorry, what is the direction of growth?
I'm sorry?
The direction of growth? What is vertical?
Vertical, yeah. So in 2005, a big step forward was made by Dew and his collaborators. They were trying to understand the role of this protein molecule. Why were there these nanospheres and how do they form? So they did an in vitro study. That's a little bit limiting because you throw out everything else. You don't worry about the mineral or anything else that might be there in vivo. Nevertheless, it's a big step forward. And they found, as I will show you, that this molecule self-assembles from monomers into eventually into nanospheres, which then fuse and form basically a scaffold around these minerals. And they sort of guide, apparently, the way these minerals grow. And here is a part of their paper. This shows a transmission electron microscope of some of the linear arrays they saw of these protein molecules. So for example, so you have this chain, complicated chain. Here is a nanosphere that makes up part of that chain. That nanosphere is about 50, I think it says 50 nanometers in diameter. If you blow that up and look closely, you can see inside there are oligomers of different sizes. And if you look in more detail at intersections of nanospheres with each other, for example, if you look where this white arrow is pointing, I've lost the white arrow, oh, there, you can see that there is a bridging taking place between the nanospheres that's beginning to lead to the formation of the nanochain. And likewise, if you look at the black arrow here, you see a fusing of these nanospheres. So what happens, they came up with through many different experiments, including scanning electron microscope and atomic force microscope. They came up with this proposed scheme. They suggested that these monomers of the protein, which are about 2.2 nanometers in size, would form dimers and trimers, hexamers, and eventually form a collection of these into a nanosphere, and those nanospheres, they said, would then eventually bridge to form these chains. Now, what is a protein molecule? What's it look like? Well, if you looked at the real structure, you would probably not think there's a shot in hell that we could simulate this. Right? So if you look at the alpha and beta sheets of this molecule, it's a far cry from what I'm showing you here. But it's basically a hydrophobic core and a hydrophilic tail. That tail is charged, and that tail is absolutely crucial. If you take away the tail, they found out that you don't get any of this taking place. In fact, we had done a study of a model very similar to this without a tail, and we found fractals. Okay? It has nothing to do with this. But you put those tails in, and you include Coulomb charges, and you can see what's happening. Of course, the Coulomb charges want to push these tails away. Those things actually act together with the hydrophobic attraction to do this self-assembly. Now, how did we come to this problem? Well, Amit Chakrabarti, who has been here and has written umpteen papers with Raoul, had visited me to give a lecture maybe 4 or 5 years ago. And he showed me this science article. And he said, look at these pictures. We ought to be able to explain this. And then we both nodded our heads and forgot about it. And then when Tony was here, and he shared an apartment with Tony's apartment, for the month, and we came up with a model. All right? And then we gave it to Wei Li, a very talented graduate student, to do a Brownian dynamic study. So what's our model? It's a typical physicist model. Okay, we treat the core as a sphere, hydrophobic sphere. Now, this experiment had been carried out very carefully under a wide variety of experimental conditions. Right? And one of the things they did was to use polyethylene glycol, which is a polymer which will induce an attraction between molecules. It's very well understood. It's used commonly in all the colloid field. And there's a very good model to mimic that force. And that's called the Asakura-Osawa model. So our model said, okay, these protein molecules have a hydrophobic core sphere, and they interact via this Asakura-Osawa potential, and we will put in exactly the parameters that were done in the experiment. Okay? Because the shape of the potential depends very much on those parameters. We then approximated the tail as a point charge. Okay? To get the tail, just put a point charge on the surface of the sphere, and you can control the strength of it. You can control the divided screening length and the amplitude of the Coulomb force, and we chose those parameters in accordance with the experiment. Those Coulomb forces will exert torques on nearby Coulomb particles, and so this will cause a rotation. So the Brownian dynamics equations that we solved were the acceleration of the particle is given by a gradient of a potential, that's the Coulomb potential between the red point charges, plus the Asakura-Osawa attraction between the spheres. Then there's a translational damping term and a random force, and then there's angular momentum, torque, etc. Okay, so we put in these into our model, solve these equations, and lo and behold, what came out was typically, not always, not all the configurations look like this, but typically what we found was that indeed what happened in this model was that our monomers formed dimers and trimers, they formed hexamers, and then hexamers and these others would get together and form a nanosphere, and then these nanospheres would touch and form these nanochains. And we characterize these nanochains in various ways, including the radius of gyration, the moments of inertia, and things of this sort, which were not done in the original experiment. But what we found was that our simple model reproduced the essence of their experiment. Now, we could not run long enough to reproduce what they saw in the later stages, which I haven't told you about. In the later stages, they found that these nano chains actually thicken and grow into ribbons, micro ribbons, and we couldn't possibly, with our computer power, simulate that. But we got the initial stages pretty right with this. Now, how am I doing on time?
2 minutes.
Okay. I don't want to go into much detail, but it turns out that if you look at the time dependence of the number of clusters, which will decrease with time as these things aggregate, and if you look at the dependence on how the radius of gyration of these clusters grows with time, it turns out that they're pretty accurately described by what's called the diffusion limited cluster aggregation model, which has been known now for 30 or 40 years. And there are exponents that go with that model, and one says that the number of clusters should be linear, inversely linear with time, which seems reasonably correct, and likewise the radius of gyration should grow like the square root of time. So that part seemed to work to be consistent.
Excuse me, Jimmy.
Yeah.
In the previous transparency, in the previous one, that's as a function of time for fixed density?
Fixed density, but the typical configurations that we saw form as in time into equilibrium.
Okay.
Equilibrium is maybe a strong, too strong a word, steady state or something. So these two measures fit reasonably well with this diffusion limited aggregation model. On the other hand, when we looked at the structure factor, if you look at large Q, and you saw this, there's a line here that is the Perot law, classic Perot law, which is well satisfied by this. But you can also look at shorter Q. The shorter Q gives you the fractal dimension of the system. And that fractal dimension that we got, now it's hard to really get precision numbers from this, was a number of about 2, whereas the diffusion limited aggregation theory predicts 1.8. So there's not a completely consistent picture here. And we think we know what's going on because the Coulomb charges, once they start to form these chains, those things do ordering on the chain. All right? So they affect, there's a surface reorganization of the chain due to the Coulomb charges, and that's not taken into account in something like a diffusion limited aggregation growth model. So it's, I guess I'm saying that this is not the whole story, okay? But this is the best we have found. I'm going to wrap this up just to tell you, we've now written the second paper, and this is where we suddenly found we were, before, literally we knew 2 papers. The science paper that Amit brought to my attention, and an earlier paper we found reference in that. When we sent out the second paper, which has just been accepted, both referees said, you guys are vastly ignorant, apparently, of the literature. And they sent us tons of references. And indeed, we were vastly ignorant of the literature. And there was pre-2005 literature, which was relevant, and there's post-2005 literature, where they're looking at in vivo studies now. And one of the referees wanted us, before we published our paper, to redo our work in vivo. To which I said, no mas. No way. But that's a really interesting problem. But what we did do was, because we knew our results depended sensibly on our choice of the Asakura-Osawa parameters and on the Coulomb strength, we wanted to see how robust our results were, and they aren't. Which probably one wouldn't expect, because the experiments, what we did was to choose our parameters to match the experiment. So what we found was that if you change the divide length, originally we had it of 0.4, we increased it so that the repulsion was much greater. What we found was that we changed well, okay, so increase the divide length. Then we systematically changed the well depth, 6, 8, and 10 kT, to see what the effect of the well depth and the repulsion range was. And what we found was that that really changed the morphology of these things. What would have been a nanosphere in our original picture ceased to be a nanosphere. It wasn't so far from it, but as we increased the well depth, you can see that we really lost the building block that these people thought was relevant. We also found that the kinetics was not quite consistent with this diffusion-limited aggregation theory as we changed these parameters. So there are a lot of open questions, which I won't go into detail. Just to stop and talk just about the amelogenin, because now that I've started to read these papers, I realize it's just a gold mine of problems out there for theorists. The biggest one is to extend our work in vivo. Now that really is going to be very difficult, because in vivo means you have to take into account the mineral, for example, that we had totally forgotten. And there's clearly some interaction that will take place between the two components, the protein molecule and the mineral. And there are other things in vivo that we don't even know about, that the biologists could tell us about. And then hopefully if we did that, we would be able to get a really detailed understanding of how that scaffolding does control the mineral growth. Right now, all we've been able to show is how a simple model can show you how the protein will self-assemble into a way that would apparently act as a scaffold. And then once you go on to other examples of biomineralization. Anyway, I will stop here and thank you very much for your patience.
In the case of the Janus particles that you use to transport drug for drug delivery, what would be the advantages of stealth deposits?
Well, probably the major advantage is efficiency and the relative ease of controlling this.
But I mean, when you shot the Janus particles with the drugs, so I understand that this density, you get these stages where the drug is inside, and that, but inside the blood, the density will be very low, and probably you don't have these spaces.
You mean once it gets delivered?
Yeah, but it's inside the blood stream. So because, well, usually you have to go through the liver, and then when you have survive to the phagocytes.
I think that's the problem with all methods of drug delivery. All of them encapsulated with something.
No, yeah, but I mean, here somehow, if I did not understand it wrongly, the encapsulation comes from the interaction between the particles. There is not a real bond between the particles. So if you lower the density, probably the species survive even at very low density, in the limit of infinite dilution.
So I think you're asking two questions. One is that they really are bound. You can control the forces.
The bond between them is of 1 kBt.
Could be you can control how much that could be. Maybe 1, 10. The second question was what happens once it enters the bloodstream. And then I really don't know. But all these methods that I know of have the same problem. I mean, there has to be a way for the encapsulation to break up and let the particle out. You're really telling me why I can't patent this. I think I thought about this, but in order to patent in the United States, you have to demonstrate that it can be done. That's good. I think the last time I was here, I was telling you about cataracts, right? And George Benedict found that cataracts happen because there's an aggregation between molecules in the eye. And there was a phase transition with a critical point. And that critical point was physiological temperature. So he's a very clever man, so he formed a company and he started putting eye drops as a test case in the solution, not in the person, to lower the critical point to say 30 degrees so that you wouldn't have the stage separation. They went through 3 stages of FDA approval. Things were looking great. And then they put the eye drop in a person, and the eye drop caused more trouble than the cataracts. It's not easy.
Second question, please. Okay, it's about this model, this nice model where you have the colored particle and then you put a point charge
Right.
to mimic the effect of the tail.
Yes.
So here you are, you say you will use long interaction, but do you use some kind of short, some cutoff, or?
Well, yes, we control the device screening mode. And we,
so it's screening, okay.
yes, it's the screening, and we chose the one compatible with the experiment in the original paper.
So they are counter ions
Yeah.
around there, okay, because otherwise, because it's periodic boundary conditions, isn't it? And
In our case, yeah.
you use periodic, but otherwise it will sample not converge.
Yeah,
Okay.
exactly.
More questions?
The concept of biomineralization is a question of aging, or a question that has to do with changes in density or temperature or anything?
By aging, you mean time.
Yeah, becoming old.
There's always nice things about you. I'm not sure I understand your question because
I mean, I have no idea. I mean, the process of biomineralization is just something that, you know, under the same temperature and the same density, just because of time.
yes, it takes place during, as far as I know, during the early stages, and somehow the scaffolding eventually gets washed out. I don't know how that happened, but these, as far as I know, these nanosphere nano chains somehow do not survive in the final dental enamel. I don't know how that final process takes place. Everyone right now has been focusing on trying experimentally and theoretically to understand how does that initial molecular stage of self-assembly take place and why.
Just a very general question, probably impossible to answer, but is there any, you have shown 2 examples of assemblies of molecules of atoms that assembles in say, structures such as the Janus particles or the protein balls, and then a second level of organization forming ribbons or forming chains or forming the do you know what is the rule for? I mean, if you put argon atoms in a box, you don't get that. And so, what makes a system of atoms to self-assemble? What is the minimal ingredient to have them to make a hierarchy of organizations?
That's a very deep question. No, that's why the word self-assemble is a cliche in the United States, and I think it's a shame because you know they're doing all it's used in every grant proposal and everything, but it doesn't address some of these basic issues. I mean, obviously the answer has to do with minimization of free energies and things of this sort, but beyond that, I can't tell you. I can write a grant with you, though.
You mentioned these amelogenin particles were fractals in your simulations.
Oh, that's an interesting thing. Before we did this, Amit and I and Wei had found a paper on drug delivery of insulin. And it was a novel paper because they proposed that instead of the standard way of preparing insulin in solution, which has some difficulties, they showed they did an experiment where they added PEG, the same thing we use here, polyethylene glycol, at the isoelectric point of insulin, and they quenched the system to a point where it formed fractals. They then broke up the fractal. There was no Coulomb charge here. Don't let me forget. So they then broke out the fractals, and they found out they form nice uniform spheres, which is what the drug industry wants, a very monodispersed set. So our attempt to explain that was to take the Onsikura model, quench it, form fractals, which we did, and then instead of stirring, I think I talked about it here, we heated it back up, which then broke it up, and then to a reasonably monodispersed set. As soon as you put the Coulomb charges into that same model, it changes the whole reorganization. that led to these whole formation of these nano chains and things. So it's a very delicate balance. Now, of course, we didn't have the same parameters in both papers, but experimentally it's known that if you take away the hydrophilic tail, this process doesn't happen, and our simulation certainly shows the same thing.
But the particles you showed experimentally are the fractals? And the nice sphere you showed at the beginning, although they
No, in this case they're not fractals. Well, not. It's hard to be precise because we have only one way of estimating it from the structure factor, and our numbers are not great. It's like critical exponents in the old days.
Okay. Any other questions? Now remember that Jim will be here almost 2 more months, so we have time to ask some questions. You have to write a proposal. And thank you again.